Welcome to module P3. This is again Faxon project. As of now, you should have completed P01, P02, P03A and P03B, and your ALU should be working. All your tests should have passed. If you have any issue in that, please do put it on the discussion forum. Don't give up. You can make it work, and it's very, very simple. Now what we will do now is to look at P04. Now working with P04 is extremely important for you to have understood this entire module 3.1 to 3.6. So we have done quite a bit of work there, especially the 3.5, 3.4, 3.5 and 3.6, where we started talking about the instruction set architecture. Now this exercise that you are going to do is very, very simple. It hardly takes another 1 hour for you to complete 2 exercises that are part of P04, and that will give you a complete understanding of the instruction set architecture that we had been talking of so far, and it will also give you very good insight into assembly programming. Assembly programming is a must for you to understand, so that later when you do embedded systems or any sort of computing, when you want actually performance, there may be a need for you to go and start looking at the assembly program. So irrespective of the discipline that you are studying, whether you are a computer scientist or electronics or anybody who wants to work in the area of embedded system or information security, there is a need for us to have an understanding of how assembly programs work, how assembly languages are formed. So this particular project will give you tremendous insight into those issues, and so please take this project very seriously and let us do that. So this will also sum up many of the things that you may not have followed in your module 3.4, 3.5 and 3.6. Right. Now let us look at, so as far as the instruction set architecture of our hack goes, there are 2 types of instructions. One is the at A or whatever at value. This is called the A instruction, and there is another instruction which is called the C instruction. Right. Already I told you, right, suppose I want to do while I is greater than 0 or while I is greater than 6000. Suppose I want to do while I is greater than 6000. I want just, that means I basically want to first check this condition I is greater than 6000. Okay. Now I can basically say, let me say that I, for our understanding, is at location 1000, memory location 1000. Every variable will be associated with a memory location. So I just say at 1000. When we say at 1000, there are 2 registers, namely A and D, and the A register will get 1000. So this is assembly, I am writing the assembly program. The moment I say M in the assembly program, it refers to M of A, that is M of 1000. So the moment I say M here, it refers to the content of the memory location 1000, which is nothing but the value of the variable I. So when I have a variable, there are 2 attributes, like if you are a human being, you have, for example, you have name and age as attributes. Like that, the variable has attributes. So if I have a variable I, for example, here, then it has an address and it also has a value. So I, this 1000 is the address of I, the content of this 1000 is the value of I, right. So there is a main memory here and there is 1000 here, right. Now let that content be 5, for example, let us start here. So if the moment I say M, this is M of the address that is stored in A, M of A, so M of 1000, so it will be 5, right. So M, essentially if I use the value M here, it essentially gives the value 5. So if I say M is equal to M plus 1 here, what essentially happens is your 5 now becomes 6. m equal to m plus 1 means your phi actually becomes 6, right. If I say d equal to m, essentially that means the register d gets the value phi. Now, I can say at whatever say 6000. The moment I say at 6000, the A register basically gets the value 6000, right. Now, we will now say d is equal to d minus A, d equal to d minus A. What is d equal to d minus A? Now, your 6000 is equal to phi equal to, now your new value of d now will become phi minus 6000, essentially this will become minus 5995, because d was originally phi, A was 6000, phi minus 6000 will become this, right. Now we can go and check. So, now we say that suppose this I is, so let us say if I is greater than 6000, do something, else do something else. So, let me say this is statement 1, set of statements, this is statement 2. Now, here if this is I is going to be less than A, I is going to be less than 6000. So, I have to go and do some statement S2. So, we will put some label here, the else label, right, and here all the statement S2 will be there, here all the statement S1 will be there, right. So, when I say d equal to d minus A, now we will go and say at else label. Else label is a symbol that we have written and we put S2 here. Now, I go and check d semicolon if it is, so if it is j is less than or equal to 0, JLE. Then I put this, the machine language corresponding to S1 here, the machine code corresponding to S2 here. Now, I will say end if label, okay. So, at this point after you finish S1, you again put at end if label and you say 0 semicolon jump. Okay. So, what happens here? First I say at 1000 d equal to m. So, 1000 I is mapped. So, d now gets the value of I, which was to start with it was 5. Okay. Now, at 6000, so A gets the value 6000. When I say d equal to d minus A gets the value minus 5995. Now, if the value d equal to d minus A is negative, that means I have to execute else, because I am comparing I with 6000. So, I have subtracted 6000 from I. If this is, if it is less than or equal to 0, then I have to execute the else part. If it is greater than 0, then I have to execute the if part. So, I just put at else label, which is the address of this location here, and I just check d JLE. If d is less than or equal to 0, JLE means less than or equal to 0, then what should I do? I should jump to the address in A. So, when I say at else label, so let us assume that we have started with 100 here, this will be 101, 102, 103, this is 104, 105, then this S1 let us assume is single statement 106, 107, 108. So, this S2 again let us, so else label is 109, end if label is 110. So, the moment I say at else label, your A now will become 109. So, now I say D JLE, D is negative, so it is less than or equal to 0. So, essentially JLE jump when less than or equal to where the address given in A, that is 109. So, I will jump to else label, execute S2 and go off. But suppose this is positive, suppose I was say instead of 5005 or 6005, right. So, when I subtract this would have given 5 plus 5. So, your D will not be negative here. Then what you do, you execute the statement S1, then you say at end if label. The moment I say at end if label is 110. So, 110 will be loaded here and 0 colon jump, 0 semicolon jump essentially says no condition to be checked, just jump. This is called an unconditional jump, there is no condition to be checked here. So, your code actually comes to end if label and finishes. So, this is how we can execute, we can translate an if else statement, right. So, the things that we need to understand here are that how do we handle the, there are some, how do we handle jumps and how do we handle conditions. So, handling jump is the major thing here. We have seen both conditional jumps and unconditional jumps, and so this is the way by which the ISA hack is used for translating a C program into this ISA language. Okay. Now, as a part of your project, so this gives you some basic understanding. As a part of your project, we have to do 2 programs. So, we will explain one program now, and the other program, the structure we will just discuss here, so that we take it forward from there. So, the program is something like this, we will just go to this. So, this is the 4th project here, there is, so we just take this mult program, there is a mult.asm that you will see there, you can open that and that is where you see this is the code. So, I have just put this code here. So, it basically says that I have R0 and R1. So, in the RAM I have R0, R1 in the locations 0 and 1, and there is R2. Let R0 store A, R1 store B, write a program that will take A and B and compute A into B and store it in R2. So, the way we are going to do is, please note that our ALU cannot do multiplication. The ALU that we have designed can do only addition. So, it can do x plus y or x and y, it can't do multiplication. So, how do we model multiplication using addition? So, if I want to do A into B, I add A B times, add A B times. This is essentially what we need to do, right. So, that is precisely what we are going to do here. So, let us look at the code very quickly. Okay. So, what I am going to do is, so this is the thing, I will copy A to R3 first, because I do not want to destroy the value of A. I will create another temp location R3, wherein I will copy this value of A, right. And then what we do is, while R3 is not equal to 0, right, R2 is equal to R2 plus R1, R3 equal to R3 minus 1. Initially I will make, let us say R2 is equal to 0, R2 is where I am going to write the sum. So, initially I will make it 0 to start with, and I will copy the value of A to R3, and while R3 is not equal to 0, I keep adding R1. So, every time I add R1 to R2, right, every time I add R1, one time R1, I reduce R3. So, the number of times R1 gets added to R2 is equivalent to A times. So, I am adding A B times, sorry. So, I can say yeah, I am adding A B times. So, this is how I can multiply, right. So, so first R2 is equal to 0, copy A to R3, while R3 is not equal to 0, keep adding R1 to this R2 again and again. How many times? R3 times, that is R1 stands for B. So, keep adding B to R2 A times, and this is the answer. So, finally, the answer will be in R2, right. So, this is the code, and now with this code let us go and see how we are going to do this program. So, first thing is first thing that we need to do is make R2 0. Let us start looking from here, R2 0. So, R2 is at RAM location 2. So, the moment say at 2, right. So, your A register gets the value 2. Now, I say M equal to 0, M of 2 actually becomes 0, that is the second location becomes 0, which is equivalent to R2 becoming 0. Now, at 0, what is stored in R0? A is stored in R0. Now, D equal to M means D equal to M of 0. So, D gets the value of A at 3. At 3 now A the register A gets the value 3. When I say M equal to 3 D, what is the address now? 3 is the address. So, M of 3 will get D, that means R3 now gets the value of A. So, I am copying the version of A into R3. So, this is what precisely we have done here. First we made R2 as 0, the next thing is I copied A from R0 to R3. So, how did I do R2 equal to 0? First I say at 2, at 2 means your A register will get the value 2. Now, I say M equal to 0, M equal to 0 essentially means M of A is equal to 0 or M of 2 is equal to 0. So, the second location here, this is 0th location, first location, second 3. Now, the next step, copy A to R3, I said at 0. So, your A register now becomes 0. Now, I say D equal to M of 0, M, D equal to M, which essentially means D equal to M of 0. So, whatever, let us say A equal to 5 and B equal to 3. So, D gets the value 5. So, D has the value 5 now. Now, I say at 3 is now pointing to R3. Now, I say M is equal to D, that this essentially means M of 3 is equal to D. So, this gets the value 5. So, I have copied a value of R0 to R3, right. So, the first two steps we have done now. The next step that we will do, we will just see here, is as follows. So, now we are going now. So, this is a loop. So, what we did, while R3 is not equal to 0, what we need to do, while R3 is not equal to 0, R2 is equal to R2 plus R1. So, where is R2? While R3 is not equal to 0, first I have to check that condition. First I am checking the condition, I am first reading R3, where is R3 stored? It is stored in M3. So, first I am taking the address 3, I am copying the content of that address 3 into the D register, D equal to R3. Now, I am comparing D whether it is equal to 0, JEQ, and when D is equal to 0, that means I have to break this loop. So, I have to jump to end. So, what I do at end, so the address register A gets the value of the symbol end, and I say D JEQ. D semicolon JEQ essentially means what? If your D register which is storing R3 is equal to 0, then jump to the address in the A register which is END. So, I just basically jump to end if D equal to 0. So, while R3 not equal to 0 is checked, this condition R3 not equal to 0 is checked here. Then what I need to do? I need to do R2 is equal to R1 plus R2 plus R1. So, first I am accessing R1 at 1. So, D equal to M. So, D has the value of R1. Then I say at 2. So, now I say M equal to D plus M. So, I may not need the semicolon, I may have the semicolon, does not matter. So, M is equal to D plus M. What is M equal to D plus M? So, what is D having? D is having the value of R1. Now, I have put at 2. So, this M now is R2, this M is also R2. So, R2 is equal to R1 plus R2, right. So, now, so I have now done that. Then finally, what I need to do? I have to decrement R3 at 3, M equal to M minus 1. After finishing it, I have to start going back to this loop. So, I put at loop here. So, this is the start of this loop into address, and I say do not check any condition, unconditional jump to loop. So, I come back here. So, by doing this, we have basically done this part of what we are trying to do here. So, while R3 not equal to 0, R2 equal to R2 plus R1, R3 equal to R3 minus R1, this we have coded. So, this is how your C program essentially gets translated to this. Now, what we need to do is, there are two interesting things that are part of this whole stuff. There are two tools that are basically available which you can use to verify whether your program is correct or not. So, let us go into this. In your go to tools, now you can take what we call as the assembler. Click on the assembler, and now we can open a file, the source file whatever you have taken. So, this is there in your take this mul.asm file. So, your file is here. Now, you can basically see how you, this is assembler. So, whatever you have written is in the assembly language or mnemonics, and that needs to be translated into binary. So, this assembler basically takes your mnemonic and gives the binary equivalent. See how it is going to do. So, the assembler has started working. So, it basically it is all comments it will ignore, as you see here. These are all comments. Okay. Now, this is the first statement, add 2. Add 2 is an A instruction. So, this is the 16 bits as you see here. The first bit is 0, I am moving, and the remaining bit is 2, 0, 0, 0, 0, 1, 0. So, that you see here. Next step, M equal to 0. M is a C instruction. So, this is 1, 1, 1, and then the this is A should be 0, and 1, 0, 1, 0, 1, 0 for C1, C2, C3, C4, C5, C6 essentially gives you 0, and then 0, 0, 1 is the destination, because it is going to M, the destination bit, and there is nothing, no jump here. So, the last 3 bits are 0. So, this is how you can interpret instruction by instruction. So, we have seen in module 3.5 how A instruction and C instructions, they are encoded, etc. So, those things you can basically analyze here and see how each instruction map onto the corresponding bit patterns of those instructions. Now, let us go ahead and do this entire thing. So, if you click on this fast forward, you will see the whole program getting compiled. Done. So, the last part we have just put at end 0 colon jump, if you see here, right. So, this is an infinite loop, this is an infinite loop, just for it to come and stop here. So, this is how, so your program is now, the assembler basically converts your mnemonic to basic machine instructions. This is whatever you are seeing here, this is what your system can understand. Now, this file, whatever, you can save this file. So, this is so you save this file, it is called, this file is mult.asm that you have coded, this file, this is called mult.hack, which the assembler has generated. Now, the next thing is, once you finish with the assembler, now you can go and do this emulator, CPU emulator. This is quite interesting, as you see here. The CPU emulator here, you can now load a program here. So, we go back to this load a program. So, I can load this hack program here, click on that load. So, now your program is basically come here. Okay. So, for example, right, okay, and note that all your symbols are also basically resolved here. This is the ASM version. Now, we can see the binary version also here. This is the binary version of the program. For readability, I can make it as an ASM version. So, all your symbols like loop, end, etc. For example, end is 18. So, your at end 0 colon jump was there, right. So, this end now has become 18. Now, your loop has become 6, because your loop started at this point and it is 6 again, right. Your end is 18 here, as you see here, your end. At this point you add an at end, which was coming here, right, when your while loop condition is satisfied. So, this is now done. So, what we are assuming is that 0 and so let us say I will make it as 5. I can go and edit this memory. So, I will make this as 3, 5 and 3 are here. Right. So, now we will run this. We can actually make it a bit faster also. So, this has come to this end loop and it is doing an infinite loop here, as you see here, but the answer that you have got is 15, 5 into 3 is 15. Okay. Now, so this is a verification that your program has actually done well, correct. But now, what we can also do is, so this is a slow fast button which will see that your simulation can be, the speed of your simulation can be, or actual animation can be faster or slower. Now, let us stop here, let us again go back here and we will start doing one by one. So, one of the interesting things that you should note here is this is the ALU, right. So, first let us start the program again, single step, add 2. So, we can say that, so this is over, so I can say stop, oh, still it is here. So, we will again load the program. Yeah. So, now we will see what is happening at 2. So, nothing happens at the ALU. Next is m equal to 0. So, your m bar A input is 2 and this becomes output ALU output is 0. So, now we are coming to at 0, okay, D equal to, so next one D equal to m, okay. That is the instruction. The moment I do that instruction D equal to m, now you say that the D register actually becomes 5, right. So, the ALU output became 5 and D register actually became 5. Now, I am doing the next step at 3. Now, I say m equal to D, right. The moment I say m equal to D, your m, this output is 5 and your D register is 5 and your location 3 also became 5. Now, again I am accessing location 3, D equal to m. So, your D register should become 5. Now, I am making at 18 D semicolon JEQ, no, your, then I am saying at 1 D equal to m. Once I finish D equal to m, your D register should get 3 and so on. So, if we can step through each one of this again and again and again, every instruction what is happening to the memory, this is the memory part, and what is happening at the ALU, you can basically see how the impact of each instruction on the memory and the ALU, and you can finish. Now, there is also another thing that we can load a script here. There is a script called mult.test. We can load that script. Now, this is a script here. So, when you look at the script, it says first load mult.hack, compare, set RAM 0 is 0, RAM 1 is 0, make both as 0, RAM 2 is -1 and run the simulation. Similarly, both as 0 and output, one of them as 1 and 0, one of them 1 and 0, then 0 and 2, 0 into 2, then 3 into 1, then 2 into 4. So, we can, and 6 into 7, 6 into 7. So, all different combinations this script will tell you, and there are certain script arguments like set RAM 0 0, set RAM 1 0, RAM 2 -1, and repeat 20 tick tock means give lot of clocks in between. So, by the time this repeat completes, your 0 into 0 would have been computed. Then it goes and restores the argument there and it checks the output. What is the output? Output, there is always a format. You output RAM 0, RAM 1 and RAM 2. RAM 0 into RAM 1 should be equal to RAM 2. So, that is also given here. So, this script is quite easy to understand, right, but now we can run the script. So, if I say run the script, now this has set RAM 0 and RAM 1 to 0, and now it is basically waiting for the simulation to complete, right. Repeat 20 times tick tock. So, I can now make it a faster also. Now, it has done 1 into 0 and it is just checking it 40 times. Then it has done 0 into 2 and it is just checking it, 3 into 1 finish, 2 into 4 finish, 6 into 7. 6 into 7 again, right, and this is done. So, basically I can run a script to verify this also, right. So, with this we have given a demo of both the assembler and the CPU emulator. We will also do another example as module P4 that we will be presenting, where we will look at yes, interface to the I/O, basically the screen. We will do that example in the next module. Thank you.